You do not need to understand every idea tonight. You can simply listen as the words move quietly through the room, one after another, without asking anything from you. If your eyes already feel heavy, you can let them close. The story will continue gently, even when your attention begins to drift. Tonight, we're going to explore something that surrounds every moment of your life, yet can never be touched or held. We're going to think about time. Time may seem simple because clocks divide it into seconds, minutes, and hours. But clocks do not create time. They only measure patterns that repeat with remarkable regularity. A clock might follow the swinging of a pendulum, the vibration of a crystal, or the changing energy of an atom. Each method gives us a steady rhythm, like a quiet heartbeat used to compare one moment with the next. For most of human history, people did not carry precise clocks. They watched shadows move across the ground, noticed the position of the sun, and followed the slow changes of the moon. Morning began when the sky brightened. Evening arrived when the light softened and the stars returned. Life moved according to the natural rhythms of Earth. The day exists because Earth rotates. As our planet turns, different parts of its surface face the sun and then move into darkness. One complete rotation takes almost 24 hours, although the exact astronomical measurement is slightly different from the day shown by ordinary clocks. Our familiar 24-hour day is connected to the sun's position in the sky. Because Earth also travels around the sun, it must rotate a little more each day for the sun to appear in the same place again. This small difference is one reason timekeeping becomes more interesting when we look closely. There is no need to hold on to every detail. You can let the facts drift past you like small lights moving slowly beyond a window. The year comes from another motion. Earth travels around the sun along a path that takes a little more than 365 days. That extra fraction of a day is why calendars sometimes need a leap year. Without occasional adjustments, the seasons would slowly move away from the dates we expect. Calendars are human systems built to stay connected with astronomical cycles. Different civilizations created different calendars, depending on whether they focused on the sun, the moon, or a combination of both. A lunar month follows the changing phases of the moon. From one new moon to the next takes about 29.5 days. Because this does not divide evenly into a solar year, lunar and solar calendars require different kinds of correction. Timekeeping is partly a study of the sky, and partly a story of human agreement. A second, for example, once depended on dividing the day into smaller and smaller parts. Today, scientists define it using the behavior of cesium atoms. These atoms produce an extremely stable frequency, allowing atomic clocks to measure time with extraordinary precision. The atoms are not tiny clocks with visible hands. Instead, their energy changes create a dependable rhythm that can be counted. This rhythm is far more regular than the movement of most mechanical clocks. Atomic clocks are so precise that their errors may remain extremely small, even across millions of years. Yet even the best clock does not explain what time truly is. It only gives us a reliable way to compare events. One event happens, then another follows. A cup cools. A shadow lengthens. A distant star changes slowly across centuries. We experience these changes as part of the flow of time, but physics suggests that time does not pass identically for everyone. According to Einstein's theory of relativity, the rate at which time passes depends partly on motion. A clock moving very quickly can measure slightly less time than a clock that remains still relative to it. At ordinary speeds, the difference is far too small for us to notice. But at speeds close to the speed of light, the effect becomes much stronger. This is known as time dilation. It has been measured using precise clocks carried on aircraft and satellites. When the clocks return, they can show tiny differences compared with clocks that stayed on the ground. These differences are not caused by broken equipment. They are part of how time behaves in our universe. Gravity also affects time. A clock closer to a massive object runs slightly more slowly than a clock farther away. Here on Earth, a clock at sea level and a clock high on a mountain do not pass through time at exactly the same rate. The difference is extremely small, but modern atomic clocks can detect it. This means your head experiences time at a slightly different rate from your feet. The effect is much too tiny to feel, and it does not change your daily life. Still, it is a quiet reminder that time is connected to where you are. Satellites used for global positioning must account for both motion and gravity. Their clocks move differently from clocks on Earth's surface. Without corrections based on relativity, navigation systems would gradually become inaccurate. A theory that sounds distant and abstract is quietly helping people find roads, ships, buildings, and familiar places every day. If your thoughts are beginning to wander, that is perfectly fine. You do not need to follow the path of every second. You can rest while the ideas continue softly in the background. In everyday life, time often feels flexible even when the clock moves steadily. A pleasant hour may seem brief. A few uncomfortable minutes may feel much longer. This is because the brain does not experience time like a mechanical device. It creates a sense of duration from attention, memory, emotion, and change. When many new things happen, the brain may store more details. Looking back, a period filled with unfamiliar experiences can seem longer because the memory contains more events. A familiar routine may leave fewer distinct memories, making weeks or months appear to pass quickly in retrospect. This helps explain why childhood summers can feel enormous in memory. So many experiences were new, and each day contained discoveries that the brain had not yet learned to treat as ordinary. As adults, repeated routines can blend together more easily. The clock has not changed, but the landscape of memory has. Attention also shapes the present moment. When you wait for something and repeatedly check the time, each minute can become noticeable. When your attention is absorbed in a gentle activity, time may seem to disappear. The brain is not counting seconds directly. It is estimating duration from changing thoughts, sensations, and surroundings. Sleep changes our sense of time even more. During deep sleep, hours may pass without any clear feeling of duration. You close your eyes in one moment, and the morning seems to arrive almost immediately. The brain remains active throughout the night, but conscious time can become wonderfully thin. Dreams may also distort duration. A dream that feels long and detailed may occur during a relatively brief period of sleep. The mind can create sequences, places, and memories without following the ordinary rhythm of waking life. Tonight, you do not need to measure how quickly sleep arrives. There is no correct minute when you must drift away. Time can move quietly without your attention. The room can remain still. The clock can continue its small repeating rhythm, and you can simply listen as the next moments arrive on their own. When we think about time, we often imagine it as a straight line moving from the past into the future. This picture is useful, but it is only one way of understanding something much more mysterious. The past feels fixed because we remember it. The future feels open because it has not yet happened from our point of view. The present seems to sit between them, always arriving and always disappearing. But the present is difficult to define with perfect precision. The moment you try to point to it, it has already become part of the past. A single instant appears to have no width, yet our experience of now seems to last for a short while. The brain gathers information across small intervals and combines it into a continuous experience. This may be why movement appears smooth rather than as a collection of separate frozen images. Your mind quietly blends sound, sight, touch, and memory into what feels like one unfolding moment. There is no need to examine that moment too closely. You can let it move gently forward without trying to catch it. In physics, space and time are often treated as parts of one larger structure called spacetime. An event is not described only by where it happens, but also by when it happens. The location and the time belong together. This idea became especially important with the theory of relativity. Different observers may disagree about the distance between events, or how much time passed between them. Yet the structure of spacetime allows those different measurements to fit together consistently. There is no single universal clock that controls the entire cosmos. Two distant observers may not always agree about whether separate events happened at exactly the same time. This is known as the relativity of simultaneity. It sounds strange because everyday life takes place at speeds far below the speed of light. Here, differences are so tiny that everyone's clocks appear to share the same present. Across enormous distances and extreme speeds, the idea of a universal now becomes less certain. Light plays an important role in this. Nothing we see arrives instantly. Light needs time to travel from an object to our eyes. When you look across a room, the delay is far too small to notice. When you look at the moon, you see it as it was a little more than 1 second ago. Sunlight takes a little over 8 minutes to reach Earth. So, the sun in the sky is always an image from several minutes in the past. The stars carry us much farther backward. A star 100 light years away appears as it was 100 years ago. Some distant galaxies are seen as they existed millions or billions of years in the past. A telescope is not only an instrument for seeing far away, it is also an instrument for looking back through time. The deeper astronomers observe into space, the earlier the universe appears. The faintest ancient light comes from a time when the universe was still very young. This light has traveled through expanding space for almost the entire history of the cosmos. It reaches us now as a quiet background glow from the early universe. You can imagine those ancient photons moving through darkness long before Earth existed. They crossed enormous distances while stars formed, planets gathered, oceans appeared, and life slowly changed. Then, after that immense journey, a few of them reached a telescope on a small blue planet. There is something peaceful about light traveling for so long without hurry. It simply continues until something receives it. Because light takes time to travel, we can never see the universe exactly as it is everywhere right now. We see a layered history. Nearby objects appear almost current, while distant objects appear increasingly ancient. The night sky is therefore filled with many different ages at once. The moon is 1 second in the past. The sun is several minutes in the past. Nearby stars are years or decades in the past. Distant galaxies may be billions of years in the past. All of these images arrive together above us, creating one quiet sky. The universe may look still, but every point of light belongs to a different moment. If your eyes are closed, you can let that sky form gently in your imagination. There's nothing you need to calculate. Just a dark space filled with soft, delayed light. Time also leaves traces inside matter. Some atoms are stable, while others slowly change into different forms. This process is called radioactive decay. Scientists can measure the remaining atoms and estimate how much time has passed. This is one way researchers determine the ages of rocks, fossils, and ancient objects. Carbon dating is useful for materials that were once alive. Other methods are used for rocks that are millions or billions of years old. The oldest minerals found on Earth contain records from the planet's earliest history. Meteorites preserve even older information. Many formed around the same time as the solar system, more than 4.5 billion years ago. By studying them, scientists can estimate when the sun and planets began to form. Time is not written in these objects as numbers. It is held in changes that occurred slowly and predictably. Layers of ice also preserve the past. In Greenland and Antarctica, snow accumulated year after year and became compressed into ice. Tiny bubbles trapped inside can contain samples of ancient air. Scientists study them to learn about past temperatures and the atmosphere. Some ice cores reach back hundreds of thousands of years. Each layer is like a faint page in a frozen archive. Tree rings offer another kind of natural clock. In many climates, a tree forms one visible growth ring each year. Wide rings may reflect favorable growing conditions. Narrow rings may reveal colder years, drought, or environmental stress. By comparing patterns across many trees, researchers can build long records of past climates. Some living trees are thousands of years old. Their oldest wood began growing before many modern cities existed. Even after a tree dies, its rings can be matched with those of older wood. This allows timelines to extend farther into the past. Coral, lake sediments, cave formations, and ocean floors also contain records of time. Nature stores history in layers. It does not remember in words, but in chemistry, structure, and gradual change. The human body contains clocks as well. Your circadian rhythm follows a cycle close to 24 hours. It helps guide sleep, alertness, body temperature, digestion, and hormone release. Light is one of the strongest signals for setting this internal rhythm. Morning light tells the brain that daytime has begun. As evening becomes darker, the body starts preparing for sleep. A small region in the brain acts as a central timekeeper. It receives information from the eyes and helps coordinate many rhythms throughout the body. Other organs and tissues also have their own local clocks. The liver, heart, muscles, and digestive system all follow daily patterns. These clocks work together, though they may respond to different signals. Food, activity, temperature, and light can all influence their timing. When daily routines become irregular, these internal rhythms may lose some of their alignment. This is one reason traveling across time zones can feel so unusual. The clock on the wall may show morning, while the body still expects night. Jet lag is not simply tiredness. It is a temporary disagreement between the external time and the body's internal rhythms. The adjustment usually happens gradually. Light exposure helps the body shift toward the new schedule. Even without clocks, people tend to maintain daily patterns. Experiments in isolated environments have shown that the human body continues producing rhythms on its own. However, these rhythms may drift slightly without signals from the outside world. Sunrise and darkness gently reset the system each day. Many animals also use biological clocks. Birds, time migration and feeding. Plants open and close flowers according to daily cycles. Ocean animals may follow the tides, the moon, or changing seasons. Some creatures respond to patterns lasting only a few hours. Others follow yearly rhythms that guide reproduction or movement across great distances. A monarch butterfly may begin a migration. It is never completed before. Its timing comes partly from inherited biological instructions and environmental signals. Sea turtles return to beaches during particular seasons. Salmon move upstream when conditions are right. Trees release leaves, seeds, or pollen according to cycles of light and temperature. Life has evolved within the repeating motions of Earth. The rotation of the planet shaped the day. The orbit around the sun shaped the year. The moon shaped the tides and brightened the night. These ancient patterns became part of living systems. Your own sleepiness tonight belongs to this long relationship between life and time. There is no need to force it. The body has been learning how to rest for longer than any human clock has existed. You can allow the rhythm to continue quietly on its own. The minutes do not need to be watched. They can pass unnoticed, one after another, while your breathing becomes a little slower and the room becomes a little more distant. The arrow of time is the name often given to the direction in which events seem to unfold. We remember yesterday, but we do not remember tomorrow. A dropped glass may shatter into pieces, yet the pieces do not naturally rise and rebuild the glass. Heat moves from warmer places toward cooler ones. Perfume spreads through a room, but does not gather itself back into the bottle. These familiar changes give time a direction. In physics, this direction is closely connected to entropy. Entropy can be understood as the number of possible arrangements hidden within a system. A neat arrangement usually has fewer possibilities. A mixed or scattered arrangement can exist in many more ways. This is why order can easily become disorder without outside effort. A carefully stacked pile can fall in many different patterns. But a fallen pile is unlikely to return to one exact arrangement by chance. The laws governing individual particles can often work in either direction. Yet when enormous numbers of particles move together, the most probable changes create a clear arrow from past to future. This arrow is statistical, rather than mechanical. It emerges from countless tiny motions that are far too small to observe individually. A warm cup of tea contains faster moving particles than the cooler air around it. As energy spreads outward, the temperatures gradually become more similar. The energy has not disappeared. It has simply become more evenly distributed and less available for useful work. This quiet spreading happens everywhere. Stars release energy into space. Engines produce heat. Bodies warm the air around them. Even thought depends on energy moving and changing inside the brain. There is no need to follow every connection. You can let the idea settle slowly. Like warmth fading from a cup beside the bed, the arrow of time may also be connected to the early universe. The universe appears to have begun in a very special state, with unusually low gravitational entropy. As space expanded, matter formed stars, galaxies, planets, and black holes. These structures may look orderly, but gravity allows entropy to increase through their formation. Black holes are especially important in this story. They contain enormous entropy, related to the area of their event horizons. This suggests a deep connection between gravity, information, and time. A black hole forms when matter becomes compressed within a very small region. Beyond its event horizon, escape becomes impossible, even for light. From far away, an object falling toward the horizon appears to slow down. Its light becomes increasingly red and faint. For the falling object, however, its own local time continues normally. Different viewpoints describe the same event in very different ways. Near a black hole, time can pass much more slowly relative to distant space. The stronger the gravity, the greater the difference. A traveler near such an object could experience less time than someone far away. This is not a trick of perception. It is a consequence of curved space-time. Fortunately, the gravity around Earth is gentle by comparison. The differences we experience are tiny. The clocks in your room remain closely synchronized. The night moves at its ordinary familiar pace. Black holes may slowly lose energy through a process known as Hawking radiation. This effect arises from quantum physics near the event horizon. For large black holes, the radiation would be extremely weak. Their evaporation could take far longer than the current age of the universe. The timescales are almost impossible to imagine. 1 billion years is already longer than human history can comfortably hold. Black hole evaporation may require numbers of years with dozens of zeros. Time in the cosmos stretches far beyond the rhythms of days and seasons. Stars also live on many different timescales. Massive stars burn their fuel quickly and may survive only millions of years. Smaller stars use their fuel more slowly and can shine for trillions of years. Our sun is roughly halfway through its stable main sequence lifetime. It has been shining for about 4.5 billion years. It is expected to continue in a similar state for several billion more. To a human life, the sun appears almost eternal, yet it also has a beginning, a middle, and a distant future. Red dwarf stars may become the longest-lived stars in the universe. They burn hydrogen so slowly that none has yet reached the natural end of its life. The universe is not old enough for us to observe that final stage directly. Every red dwarf we see is still somewhere in its long beginning. Some may continue shining after the sun is gone. Long after familiar constellations have changed, these faint stars may remain. They will offer small islands of light in an older and darker universe. Time changes the night sky gradually. Stars move through the galaxy, even though their motion is difficult to notice during one lifetime. Over thousands of years, constellations slowly lose their familiar shapes. The stars of the Big Dipper were not arranged exactly the same way in the distant past. They will look different again in the distant future. The North Star is not permanently fixed as the northern guide. Earth's axis slowly changes direction through a motion called precession. This cycle takes about 26,000 years. As the axis shifts, different stars come close to the celestial North Pole. Thousands of years ago, another star served as a northern marker. Thousands of years from now, the sky will have a different pole star again. Earth also changes its orbit in slow cycles. The shape of the orbit, the tilt of the axis, and the direction of that tilt vary over long periods. These cycles influence how sunlight is distributed across the planet. They can contribute to major climate patterns, including the timing of ice ages. The changes are gradual and predictable. They are part of the long breathing rhythm of Earth's journey around the sun. Continents move on even longer timescales. Tectonic plates shift only a few centimeters each year. That is about the speed at which fingernails grow. Yet across millions of years, this small motion moves oceans and rearranges continents. Mountains rise where plates collide. Seafloors spread where plates move apart. Earth's surface is always changing, even when the ground feels completely still. The Atlantic Ocean continues to widen slowly. The Pacific Ocean is generally becoming smaller. In the distant future, today's map of the world will no longer exist. Continents may join again into another supercontinent. This has happened before. Pangea was only the most recent of several great continental gatherings. Rocks preserve evidence of ancient worlds. Marine fossils can be found high in mountains because those rocks once formed beneath seas. Desert sandstones may appear in places that were once tropical. Coal can reveal forests that grew under climates very different from those of today. Time turns landscapes into records. A quiet hillside may contain the remains of vanished oceans. A cliff may hold layers deposited across millions of years. A single stone may be older than almost every visible feature around it. Some crystals grow over immense periods. Others form quickly when conditions change. Stalactites in caves develop as mineral-rich water leaves tiny deposits behind. Their growth may be only a fraction of a millimeter each year. Over centuries, those small deposits become long, delicate shapes. Caves therefore contain a kind of slow motion. Water falls. Minerals remain. Stone grows almost too gradually to notice. Human beings live within much shorter scales. A heartbeat lasts about a second. A breath takes several seconds. A night of sleep passes in hours. A lifetime unfolds across decades. These durations feel large because they match the scale of the mind and body. The brain is designed to notice changes useful for survival. It responds quickly to movement, sound, light, and touch. It does not naturally feel the movement of continents or the aging of stars. Science allows us to borrow other timescales. With instruments and mathematics, we can observe processes too fast or too slow for ordinary senses. High-speed cameras reveal wings bending during flight. Time-lapse photography shows flowers opening and clouds forming. Telescopes and geological records reveal changes lasting billions of years. Changing the scale of time can transform familiar things. A growing plant becomes a graceful movement. A storm becomes a brief spiral of clouds. A city becomes a flickering pattern of construction, travel, light, and decay. Even mountains appear temporary when viewed across enough time. At smaller scales, some events happen almost instantly. Light crosses a room in only a few billionths of a second. Chemical reactions can begin in fractions of a second. Particles may exist for such short periods that special detectors are needed to reveal them. The smallest meaningful unit of time in some physical theories may be the Planck time. It is an extraordinarily tiny interval, far beyond anything clocks can directly measure. Below that scale, our usual understanding of space and time may no longer apply. Physicists do not yet have a complete theory describing what happens there. Time remains one of the places where our knowledge becomes quiet and uncertain. That uncertainty does not make the universe less beautiful. It leaves room for wonder without requiring an answer tonight. You do not need to travel from the smallest instant to the oldest star. You can remain here, in this ordinary room, with one gentle moment following another. The larger clocks of nature will continue without attention. Stars will move. Rocks will change. The earth will turn toward morning. And while those vast rhythms continue, your own sense of time can soften, loosen, and begin to disappear into sleep. Human beings have always tried to divide time into useful pieces. Days and nights were easy to notice, but smaller divisions required imagination and agreement. Ancient people watched shadows move across marked stones and early sundials. As the sun crossed the sky, the shadow changed length and direction. This allowed daylight to be divided into sections, though the hours were not always equal throughout the year. In summer, a daylight hour could be longer than a daylight hour in winter. Equal hours became more practical when mechanical clocks appeared. Water clocks offered another way to measure passing time. Water flowed from one container to another at a controlled rate. The changing level could mark intervals during the day or night. Sand clocks followed a similar idea. Fine grains passed through a narrow opening, creating a simple and visible measure of duration. These devices did not depend on sunlight. They could measure time indoors, during darkness, or beneath cloudy skies. Fire was also used as a clock. Marked candles burned lower at a roughly predictable rate. Incense clocks measured time through slowly burning trails of fragrant material. Some were designed to release a sound when the flame reached a particular point. Long before digital displays, time could be heard, smelled, watched, or felt through changing objects. Mechanical clocks transformed timekeeping by using stored energy and repeating motion. Weights, springs, gears, and escapements created steady cycles. The escapement released energy in small, controlled steps. This produced the familiar ticking sound associated with many clocks. Each tick was a tiny interruption. Together, those interruptions created an orderly rhythm. Early mechanical clocks were not especially precise. They might lose or gain many minutes in a day. Still, they changed how communities organized work, prayer, trade, and travel. Public clocks allowed many people to follow the same schedule. Time gradually became less personal and more shared. The invention of the pendulum clock greatly improved accuracy. A pendulum swings with a regular period, determined mainly by its length and gravity. Its calm, repeating motion made it useful for measuring seconds. Temperature could still change the pendulum's length and affect the clock. Clockmakers developed new materials and designs to reduce these errors. The pursuit of precision became a quiet engineering journey lasting centuries. Marine navigation created one of the greatest challenges in timekeeping. Sailors could estimate latitude by observing the sky. Longitude was much harder to determine. To calculate longitude, a ship needed to know the time at a reference location while also measuring local time. A clock carried across the ocean had to remain accurate despite motion, temperature, humidity, and changing pressure. The development of reliable marine chronometers made long voyages safer. A precise clock could help reveal a ship's eastward or westward position. Timekeeping became a way of finding a place on Earth. Even now, time and location remain deeply connected. Modern navigation systems compare signals from several satellites. Each signal includes extremely precise timing information. A receiver calculates how long the signals took to arrive. From these tiny differences, it estimates distance and position. The map on a phone depends on clocks accurate to billionths of a second. The ordinary act of finding a quiet street relies on timing measurements too small to feel. There is no need to imagine all the calculations. You can simply picture invisible signals crossing the night, each carrying a small piece of time. The creation of time zones was another response to travel and communication. Before railways, many towns used their own local solar time. Noon occurred when the sun reached its highest point in that location. A town a short distance away might keep a slightly different time. This caused few problems when journeys were slow. As trains connected distant cities, schedules became difficult to coordinate. Standard time zones allowed larger regions to share the same clock. The boundaries were shaped by geography, politics, and practical needs. They do not follow longitude perfectly. Some countries use a single time zone across a very wide area. Others divide their territory into several zones. A few time zones differ from their neighbors by 30 or 45 minutes. Clock time is therefore partly astronomical and partly social. The international date line adds another curious feature. Crossing it changes the calendar date by 1 day. The line bends around countries and island groups to avoid unnecessary divisions. Nothing physical happens at the boundary. The ocean does not change, and the sky does not jump. Only the agreed date changes. A traveler can leave one place on Monday and arrive somewhere that calls the same moment Tuesday. Or the calendar may move backward, returning to a date already experienced. Day, Haups, has not reversed. Only the naming system has shifted. Calendars contain many similar compromises. The months do not all have the same number of days. The 7-day week does not divide evenly into a year. Leap days are inserted to keep the calendar aligned with Earth's orbit. Even this system is not perfectly exact. Certain century years are not leap years unless they are divisible by 400. These corrections keep seasonal dates from drifting too quickly. A calendar is not the sky itself. It is a carefully maintained bridge between human life and planetary motion. The names of months preserve pieces of history. Some come from ancient gods, rulers, festivals, or older numbering systems. September once meant the 7th month, though it is now the 9th. October, November, and December also carry names based on numbers that no longer match their positions. The calendar remembers earlier arrangements. Even after the structure changed, the week has its own long history. 7 days may have been influenced by the visible celestial bodies known to ancient observers. The sun, moon, and 5 visible planets each became associated with a day. Different languages still preserve traces of these connections. The modern week is now a global social rhythm. Workdays, weekends, rituals, markets, and schools all follow its repeating pattern. Unlike the day, month, and year, the week has no exact astronomical cycle. It continues because people continue agreeing to count it. Disagreement is so strong that the sequence has survived migrations, reforms, and changing empires. A Tuesday follows a Monday because countless people quietly maintain the same pattern. Minutes and seconds are also inherited divisions. The number 60 was useful in ancient mathematics because it can be divided by many smaller numbers. 60 divides evenly by 2, 3, 4, 5, 6, 10, 12, 15, 20, and 30. This made it practical for measuring angles in time. A full circle contains 360 degrees, while an hour contains 60 minutes. The same mathematical tradition shaped both clocks and geometry. The word minute originally referred to a small division. The second was the second small division of an hour. Names that now feel ordinary began as descriptions of fractions. For centuries, most people did not need to measure seconds in daily life. Minutes were precise enough for many activities. Industrial work, science, transportation, and communication gradually made smaller units more important. Today, computers operate on intervals far shorter than a second. Processors complete billions of cycles during one human heartbeat. Financial systems, networks, and scientific instruments synchronize events across great distances. Modern life depends on timing that remains mostly invisible. Inside a computer, a clock signal coordinates operations. It tells different parts when to move information and perform calculations. This electronic rhythm is not the same as a clock on the wall, yet it serves a related purpose. It creates order by giving processes a shared sequence. Without timing, complex systems can lose coordination. Music also depends on time. Rhythm organizes sound into repeating patterns. A beat creates expectation. Silence between notes becomes part of the composition. A melody can feel relaxed or urgent depending on tempo. The same notes played more slowly may create an entirely different mood. The brain predicts musical timing and notices when a beat arrives early or late. Gentle, steady rhythms can feel soothing because they offer regularity without surprise. Lullabies often use simple patterns and slow pacing. Their movement resembles rocking, breathing, or a calm heartbeat. Speech has rhythm as well. Pauses give meaning to sentences. A phrase spoken quickly may feel energetic. The same phrase spoken slowly can feel thoughtful and intimate. Bedtime storytelling uses time not only as a subject, but as a tool. Words arrive with enough space for the mind to rest between them. Breathing follows its own timing. The exact rhythm changes with activity, emotion, posture, and sleep. As the body relaxes, breathing often becomes slower and more regular. You do not need to control it closely. The body adjusts the rhythm automatically, responding to changing levels of oxygen and carbon dioxide. A breath begins, reaches its quiet turning point, and gently releases. Then another begins. The cycle continues without counting. The heart also changes its timing from moment to moment. A healthy heartbeat is not perfectly mechanical. The intervals vary slightly with breathing and nervous system activity. This natural variation reflects the body's ability to adapt, even within a steady rhythm. Life contains small changes. Perfect repetition belongs more easily to machines than to living organisms. Biological time is flexible. Hunger, fatigue, concentration, and emotion all rise and fall in cycles. Some cycles last seconds, others last hours, months, or years. The body is not governed by one clock, but by many overlapping rhythms. The mind also divides life into chapters. A new home, a friendship, a season, or a difficult change can become a boundary in memory. Events before that boundary may feel distant. Events after, it may feel part of a new period. This is sometimes called subjective time. It is shaped by meaning rather than measurement. A single conversation may remain vivid for decades. An ordinary month may leave almost no distinct trace. Memory does not store every moment equally. It selects, compresses, connects, and sometimes changes details. Remembering is not simply opening a perfect recording. The brain reconstructs the past using fragments and present understanding. Each memory can be influenced by later experiences. This means our personal past is stable in some ways and flexible in others. The event has ended, but its meaning may continue to change. A place remembered from childhood may feel smaller when visited as an adult. A difficult period may later appear important because of what followed. Time adds perspective by changing the position from which we look back. Anticipation shapes the future in a similar way. The brain imagines possible events before they occur. It rehearses conversations, plans journeys, and predicts outcomes. These imagined futures can influence choices in the present. Humans are unusual in how far ahead they can plan. We plant trees that may outlive us. We preserve knowledge for people not yet born. We build instruments designed to gather information for decades. Science itself is a conversation across generations. One person asks a question. Another improves the method. Someone much later finds an answer. Time allows knowledge to accumulate slowly. No single mind needs to hold the entire journey. Tonight, there is nothing you need to preserve. The ideas can pass through without becoming memories. Some may remain. Others may fade before the next sentence arrives. Both are perfectly fine. A clock may still be moving somewhere nearby. Its hands may be crossing the same familiar circle, but you do not need to follow them. The night does not require your attention to continue. Seconds can gather into minutes. Minutes can soften into sleep. And time can carry the story onward while you rest. The future often feels like a place waiting somewhere ahead. Yet from the perspective of physics, the future may be less like a distant location and more like a region not yet reached by our experience. We move through events, one moment at a time. The order feels natural because causes appear before their effects. A stone is released before it falls. A match is struck before the flame appears. A question is asked before an answer is given. Causality gives structure to time. It prevents events from becoming a meaningless collection. In relativity, cause and effect are connected by the speed of light. An influence cannot travel through ordinary space-time faster than light. This limit creates boundaries around what can affect a particular event. Physicists sometimes describe these boundaries using a light cone. The past light cone contains events that could have influenced the present. The future light cone contains events that the present could someday influence. Everything outside those cones is too distant for light to connect within the available time. This does not mean those places are unreal. It only means their events cannot yet exchange information with this moment. You can imagine each point in the universe surrounded by a quiet cone of possibility. Some events can reach us. Others remain beyond contact. As time passes, more distant regions can enter our observable history. The observable universe is limited partly by the age of the cosmos. Light from extremely distant places has not had unlimited time to reach Earth. We can only see regions whose light has completed the journey. Beyond that boundary, there may be more universe. Its light may simply be too far away to have arrived. The edge of the observable universe is not a wall. It is a horizon created by distance, expansion, and time. Every observer has a horizon centered on their own location. A distant galaxy would see its own observable region. It would not place Earth at the center. In this way, the universe has no preferred viewing point. Every location receives a different collection of ancient light. Cosmic expansion makes these horizons even more interesting. Space itself is stretching between distant galaxies. Some regions are now receding so quickly that light emitted today may never reach us. This does not mean those galaxies are moving through nearby space faster than light. It means the space between us is expanding over enormous distances. There may be galaxies whose old light we can still see, while their present state can never become visible to us. Their ancient images remain in the sky, but their future has passed beyond our reach. The universe contains places we can remember through light, but may never observe again in a newer form. This is a strange kind of cosmic separation. It happens slowly, across scales far beyond human life. Nothing disappears suddenly from the night. The changes unfold over billions of years. For now, the sky remains full of ancient messages. Each photon arrives after a journey that cannot be repeated in exactly the same way. The light enters a telescope, a camera, or an eye. Then that particular journey is complete. There is no need to feel sad about its ending. Every arrival becomes part of another event. Energy changes form. Information enters a new system. The universe continues through transformation rather than stillness. At the quantum scale, time appears in ways that remain difficult to understand. Quantum theory describes probabilities for what may happen. A particle can be represented by several possible states until a measurement is made. The theory predicts experimental results with extraordinary accuracy. Yet physicists still debate what those probabilities mean about reality. Time usually enters quantum equations as a background parameter. In relativity, however, time is flexible and connected to gravity. Bringing these two descriptions together is one of the great unsolved problems in physics. A complete theory of quantum gravity may change how we understand time at the deepest level. Some ideas suggest that time may not be fundamental. It might emerge from relationships between changing systems. In this view, the universe would not require one master clock beneath everything. Time could arise because one process changes relative to another. A pendulum moves compared with the room. A planet changes position compared with the stars. A thought follows another thought inside the mind. Without change, the meaning of time becomes difficult to define. Imagine a universe containing nothing that moved or transformed. There would be no clock, no sequence, and no observable difference between one moment and the next. It is unclear whether time would still have practical meaning there. Perhaps time and change are inseparable. Or perhaps time exists independently, even when nothing happens. Science has not given a final answer. Questions like this can remain open without becoming uncomfortable. They are quiet spaces in our understanding. You can let them remain unanswered as you rest. Philosophers have also explored whether only the present is real. One view, called presentism, suggests that the past no longer exists, and the future does not yet exist. Only the current moment is real. Another view imagines all moments as parts of a larger space-time structure. In this block universe, past, present, and future may all belong to the same complete geometry. Our awareness would still experience events in sequence, but the whole history of space-time might exist as one four-dimensional pattern. This idea can feel unusual because consciousness seems to move. We remember earlier events and anticipate later ones. We never experience an entire lifetime at once. Some physicists find the block universe compatible with relativity. Others remain cautious about what physics can truly say about existence. A mathematical model can describe relationships between events. It does not always settle philosophical questions about what is real. The difference between a model and reality is important. A map can represent a landscape without becoming the landscape. A clock can represent duration without explaining why duration exists. An equation can predict change without telling us what change feels like. Human experience adds another layer. We do not only measure time, we live inside it. Waiting, remembering, growing, healing, and learning all depend on duration. Some changes need time because their processes cannot be rushed. A seed must divide cells and build roots. A wound must replace damaged tissue. A language must become familiar through repeated exposure. Trust often develops through many small experiences. Knowledge settles through revisiting and forgetting. Time is not only a limit, it is also a condition that allows complex things to form. Stars need time to fuse elements. Planets need time to gather. Life needs generations to evolve. Brains need years to develop memory, language, and imagination. Many beautiful structures are products of slow accumulation. A seashell forms one thin layer at a time. A forest grows through seasons of light, rain, decay, and renewal. A river shapes stone through countless small movements. The result may look still, but its form contains a history of motion. Patience can be understood as respect for processes that unfold at their own rate. The universe rarely moves according to human urgency. Clouds gather when conditions allow. Fruit ripens through chemistry. Sleep arrives through gradual changes in the nervous system. Trying to force these rhythms often makes them harder to notice. Tonight, you do not need to make sleep happen. You can give it time to appear. The body can move toward rest through many small adjustments. Muscles release a little tension. Thoughts become less organized. Sounds lose some of their sharpness. Awareness begins to drift from one idea to another. There may not be a single moment when wakefulness ends. Sleep can arrive as a gradual change in the texture of consciousness. The boundary may be crossed without being observed. You may still hear a sentence while its meaning becomes unclear. An image may form without a deliberate choice. A thought may begin and then quietly disappear. This is one of the gentlest transitions in human experience. It happens every night, yet remains difficult to witness directly. The moment of falling asleep is usually remembered only as an absence. There is a final waking memory. Then time passes without a clear record. Morning appears on the other side. During sleep, The brain continues moving through cycles. Light sleep, deep sleep, and dreaming repeat in patterns across the night. These stages are not rigid boxes. They flow into one another. A typical cycle lasts roughly an hour and a half, though the timing varies between people and across the night. Deep sleep is often more common earlier. Dream-rich sleep becomes longer toward morning. The body changes its priorities as the hours pass. Memory processing, tissue repair, hormone release, and immune activity all follow nighttime rhythms. Sleep is not empty time. It is active biological time with a quieter form of awareness. The brain reorganizes information while the conscious mind rests. Some memory becomes stronger, others may weaken. Emotional experiences can be processed in new contexts. The exact functions of sleep are still being studied. There is no single explanation for everything it does. Its importance appears across nearly every system of the body. Even simple organisms show periods of reduced activity resembling sleep. This suggests that rest is an ancient biological strategy. It existed long before bedrooms, clocks, or written stories. Your body belongs to that deep history. It knows more about sleep than the waking mind needs to know. There is no need to supervise the process. Time can do some of the work for you. A few minutes of quiet can change the balance of the nervous system. A repeated rhythm can become familiar. A familiar voice can fade into the background. The mind does not need to switch off all at once. It can become less interested in holding each idea. The facts may begin to overlap with imagination. The edges between science and dreaming may soften. A galaxy may become a pattern of light behind closed eyes. A clock may become a distant pulse. A river of time may become nothing more than a gentle feeling of movement. You can let that movement carry you. There is no destination you need to reach tonight. The next moment will arrive without effort. Then the next. And somewhere between them, without needing to notice exactly when, sleep may quietly begin. Time can also be studied through the history of the universe itself. When astronomers observe distant galaxies, they do not only measure where those galaxies are, they also measure how quickly the space between galaxies is expanding. This expansion gives the universe a history. By studying it, scientists can estimate how long the cosmos has been changing from its earlier, hotter state. The current estimate places the age of the universe at about 13.8 billion years. That number is difficult to imagine directly. It is much longer than the history of Earth, life, or any human civilization. Still, the universe carries traces of its age in light, motion, and matter. The oldest light we can observe comes from a time about 380,000 years after the beginning of cosmic expansion. Before that period, the universe was hot enough for light to scatter constantly from charged particles. It was more like a glowing fog than a transparent night sky. As the universe cooled, electrons joined with atomic nuclei. Light could then travel more freely through space. That ancient light still surrounds us today. Expansion has stretched its wavelengths into microwaves, making it invisible to human eyes. Sensitive instruments detect it as the cosmic microwave background. Tiny variations in this background reveal differences in density in the young universe. Those small differences later grew into galaxies and clusters. The largest structures in the cosmos began from very subtle patterns. Gravity worked slowly. Matter gathered around slightly denser regions. Over immense periods, stars formed, galaxies grew, and empty spaces expanded between them. The universe did not begin with the familiar sky, already complete. It developed through layers of change. The first stars may have formed a few 100 million years after the beginning. They were probably very different from many stars we see today. They formed from hydrogen and helium, with almost none of the heavier elements found on Earth. Inside those early stars, nuclear reactions created new elements. When massive stars died, they released those elements into surrounding space. Later generations of stars formed from richer material. Carbon, oxygen, silicon, iron, and many other elements became more common over time. The atoms in your body belong to this long chemical history. Some were formed in stars. Others were produced during violent stellar events. They traveled through space before becoming part of clouds, planets, oceans, plants, and living cells. Matter can carry a history without carrying a memory. An atom does not remember the star where it formed, yet its existence reveals that earlier stars had time to live and change. The universe needed generations before rocky planets like Earth could appear. Our solar system formed about 9 billion years after the beginning of cosmic expansion. By then, the galaxy already contained many cycles of stellar birth and death. The sun formed from a cloud enriched by older stars. Small dust grains began to collide and stick together. Over time, those grains became larger bodies. Gravity gathered them into planets, moons, asteroids, and comets. Earth's formation was not a single moment. It was a long process of collision, heating, separation, and cooling. Early Earth was far more violent than the planet we know today. Large impacts reshaped the surface. Radioactive elements released heat. Dense metals sank toward the center, while lighter materials formed the outer layers. The moon likely formed after a major collision between the young Earth and another planetary body. Debris from that event gathered into orbit and gradually became the moon. The exact details remain an active area of research. The broad evidence suggests that Earth and Moon share a closely connected origin. The young Moon was much closer to Earth than it is now. Tidal forces cause it to move gradually outward. It is still receding by a few centimeters each year. At the same time, the tides slightly slow Earth's rotation. Ancient days were shorter than modern days. Hundreds of millions of years ago, Earth completed a rotation more quickly. A year still depended on the orbit around the sun, but it contained more days. Some fossil corals preserve daily and yearly growth patterns. These patterns help scientists estimate how many days belonged to an ancient year. Time can therefore be recorded in the growth of creatures that lived in vanished seas. The moon's slow movement changes eclipses as well. Today, the moon and sun appear almost the same size in our sky. This allows total solar eclipses when the moon briefly covers the bright surface of the sun. In the distant past, the moon appeared larger because it was closer. In the distant future, it will appear smaller. Eventually, total solar eclipses will no longer occur in the same way. Annular eclipses, leaving a bright ring of sunlight, will become more common. This change is extraordinarily slow. Many millions of years will pass before the effect becomes complete. For human observers, the present arrangement feels permanent. On cosmic scales, it is only a temporary geometry. Many things that seem fixed are actually passing through a long phase. The shape of a coastline is temporary. The brightness of a star is temporary. The length of a day is temporary. Even the arrangement of planets changes slightly through gravitational interaction. Stability in nature often means slow change rather than no change. Some systems remain recognizable because their changes happen gradually. A forest may appear steady while individual trees grow, fall, and are replaced. A body remains itself while cells are renewed and molecules move through it. A city keeps its name while buildings, streets, and generations change. Continuity can exist without perfect permanence. The same may be true of personal identity. You are not made from exactly the same material throughout life. Cells change, memories shift, and the body develops. Yet experience connects earlier and later versions into one continuing story. Time allows identity to be both stable and changing. The photograph captures one appearance. A memory holds one perspective. Neither contains the whole person. The living self continues beyond each frozen image. Photographs can make time feel especially visible. An old image preserves light from a moment that cannot return in exactly the same form. The people may have changed. The room may no longer exist. The objects may have been moved or lost. Yet the pattern of light remains. A photograph is not the past itself. It is a physical trace created during the past. Sound recordings preserve another kind of trace. Vibrations are translated into patterns that can be stored and reproduced later. A voice spoken decades ago can move air in a room today. The original sound ended long ago, but information about its shape survived. Writing carries time across even greater distances. Marks on stone, clay, paper, or screens allow thoughts to outlast the moment of speech. A person can read words written before they were born. The writer and reader occupy different times, yet language creates a connection. Books are quiet structures for delaying a conversation. A thought waits inside symbols until another mind gives it sound again. Scientific knowledge also depends on preserved records. Measurements gain meaning when they can be compared across years. Astronomers photograph the same region of sky at different times. Geologists compare layers formed in different eras. Biologists track changes across generations. A single observation is a point. Repeated observations create a timeline. Some events reveal themselves only through patience. A slow-moving object may appear still in one image. Across many images, its path becomes visible. A star may seem constant during one night. Years of measurements may reveal cycles, companions, or gradual change. Long-term observation has discovered planets around other stars. When a planet passes in front of its star, the star's light may dim slightly. If the dimming repeats at regular intervals, it can reveal the planet's orbit. The timing of these passages must be measured with care. A planet may complete an orbit in days, months, or years. Some distant worlds take much longer. Researchers may wait through many cycles before becoming confident. Science often moves at the pace allowed by the phenomenon. Not every question can be answered quickly. Some experiments run for decades. Some observatories gather data across entire careers. Some predictions are tested only after technology improves. The delay does not make the work meaningless. It is part of learning how nature changes. There is something gentle in the idea of an unanswered question being passed forward. One generation may build an instrument. Another may collect the observations. A later generation may understand what the data means. Knowledge does not belong to one moment. It can grow across time like a very slow tree. Human time feels different because life is finite. The awareness that moments will not repeat gives them weight. A familiar evening may seem ordinary while it happens. Years later, it may become precious in memory. The value was not added afterward. It was present, though perhaps unnoticed. Attention changes how deeply a moment is experienced. This does not mean every second must be appreciated. That would create another kind of pressure. Most moments are allowed to pass quietly. They support life without becoming significant memories. A peaceful day may contain hours that leave no clear record. That does not make them wasted. Rest often works in ways that are difficult to remember. You may not recall the exact moment your muscles relaxed. You may not know when your thoughts became less tense. The benefit can remain even when the process is forgotten. Sleep is full of useful time that consciousness does not record. The body repairs and reorganizes without making a story about it. Silence also has duration. A pause is not empty simply because nothing obvious happens. During silence, sounds fade, expectations settle, and the nervous system adjusts. A quiet room continues changing in subtle ways. Air circulates, surfaces cool. Distant noises appear and disappear. The building shifts slightly as materials respond to temperature. Night has its own slow activity. Outside, nocturnal animals may begin moving. Plants continue chemical processes in darkness. Clouds cross regions that no one is watching. Earth rotates beneath stars that seem almost still. The world does not stop when human schedules become quiet. It enters another rhythm. That rhythm may now be surrounding you. There is no need to decide how much time has passed. The clock can remain outside the story. You can allow this part of the night to become unmeasured. A sentence can fade before it reaches its end. A thought can lose its name. The distance between ideas can become softer and wider. Time does not need to be counted in order to carry you forward. It can move like a calm current beneath a resting boat. You may notice the motion, or you may forget it completely. Either way, the current continues. The universe has spent billions of years becoming this particular night. Stars formed and disappeared. Planets gathered. Life learned to sleep. And now these minutes can be simple. They do not need to become important. They only need to pass gently, while the mind becomes quieter and the body moves closer to rest. Time can also be found in the small delays hidden inside ordinary experience. When you hear a sound, the vibration has already traveled through air before reaching your ears. When you see a person across a room, the reflected light has already crossed the distance between you. These delays are usually too small to notice. The world appears immediate because the brain combines information arriving at slightly different moments. Sound travels much more slowly than light. This is why lightning is seen before thunder is heard. Both begin during the same electrical event, but the light reaches you almost instantly. The sound moves through the atmosphere at a far gentler speed. By counting the seconds between the flash and the thunder, you can estimate how far away the storm is. Each few seconds represents roughly another kilometer of distance. The method is simple, but it reveals something profound. Distance becomes visible through time. A delay can tell us where an event occurred. Animals also use timing to understand their surroundings. Owls compare tiny differences in when sound reaches each ear. These differences help them locate movement in darkness. Humans use a similar process without consciously noticing it. A sound from the left reaches the left ear slightly earlier than the right. The brain reads this difference and creates a sense of direction. The interval may be only a fraction of a millisecond, yet the nervous system can use it to build a three-dimensional world of sound. Bats rely on even more precise timing. They send out high-frequency calls and listen for returning echoes. The delay between the call and the echo reveals distance. Changes in the echo reveal shape, texture, and motion. In complete darkness, a bat can navigate through timing. Dolphins use a related form of echolocation underwater. Clicks travel through water, reflect from objects, and return carrying information. The returning pattern helps the animal understand what lies ahead. A fish, a rock, or another dolphin creates a different echo. Time becomes a way of sensing space. Modern technology uses the same basic idea. Radar sends radio waves outward and measures how long they take to return. Sonar uses sound and water. LiDAR uses pulses of light. These systems can map landscapes, measure speed, and detect distant objects. A short pulse leaves, travels, returns, and becomes a measurement. The interval between departure and arrival contains the answer. Astronomers also use timing to measure great distances. Radar signals have been sent toward nearby planets and asteroids. By measuring the round-trip travel time, scientists can estimate how far away the object is. The same principle that locates a wall in a dark room can help measure the solar system. The difference is only the scale. Light may need minutes or hours to complete the journey. Signals sent to spacecraft also require time. A command sent to a rover on Mars does not arrive immediately. Depending on the positions of Earth and Mars, the delay can range from several minutes to more than 20 minutes each way. A person on Earth cannot steer the rover as though driving a nearby car. The rover must perform many actions on its own. Engineers send instructions, then wait for confirmation. The response belongs to an earlier moment on Mars. By the time it arrives, the rover has already continued into its future. Space exploration teaches patience through physics. Question is sent outward. Silence follows. Then an answer returns from the past. The farther a spacecraft travels, the longer the silence becomes. Signals from the outer planets may take hours to reach Earth. A spacecraft at the edge of the solar system can feel almost like a message placed into a very slow river. The information continues moving, even when no one can hurry it. There is no need to follow every journey tonight. You can let the signals travel without waiting for them. The darkness between question and answer can remain peaceful. Pulsars offer another form of cosmic timekeeping. A pulsar is the dense remnant of a massive star. It rotates rapidly and sends beams of radiation into space. If one beam sweeps across Earth, telescopes detect a repeating pulse. Some pulsars rotate many times each second. Their rhythms can remain remarkably stable. Astronomers use these pulses to study gravity, motion, and the space between stars. The timing must be measured with extraordinary care. A pulse arriving slightly early or late may reveal hidden information. It could show that the pulsar is moving around another star. It could reveal the influence of a planet. It may even help detect gentle waves passing through space-time. Gravitational waves are ripples created by accelerating massive objects. Colliding black holes and neutron stars can produce waves strong enough to reach Earth. The effect is still incredibly small by the time it arrives. Sensitive instruments measure tiny changes in distance as space-time stretches and compresses. In another method, astronomers observe networks of pulsars across the galaxy. A passing gravitational wave can alter the arrival times of their pulses in a coordinated pattern. The galaxy becomes part of a vast natural detector. Dead stars act as distant clocks. Their small timing changes reveal motions in the fabric of spacetime. The universe contains clocks that were never designed as clocks. Stars pulse. Planets orbit. Moons circle planets. Atoms vibrate. Particles decay. Each repeating process can become a measure of duration. A clock is simply a system whose changes are regular enough to count. Some natural clocks are imperfect. Earth's rotation is not completely steady. The length of the day changes slightly because of tides, atmospheric motion, ocean currents, and movements inside the planet. These changes are very small, but precise timekeeping can detect them. Atomic time remains more uniform than astronomical time. To keep civil clocks reasonably aligned with Earth's rotation, timekeepers have sometimes added leap seconds. A leap second is an extra second inserted into the official timescale. It prevents a difference between atomic clocks and Earth's rotation from growing too large. This practice has created technical challenges for computer systems. Many systems assume that every minute contains exactly 60 seconds. An unexpected extra second can disturb software, networks, and databases. Human timekeeping becomes complicated when the planet refuses to rotate with perfect regularity. Even the shape of Earth changes slightly. Tides raise and lower the oceans. The solid planet also bends under the gravitational pull of the moon and sun. Large earthquakes can redistribute mass and alter the rotation by a tiny amount. Seasonal winds and currents shift weight around the globe. Earth is not a rigid clock. It is a living physical system with subtle variations. The moon plays a major role in slowing Earth's rotation. Tides create friction as ocean water moves across the planet. Some rotational energy is transferred to the moon's orbit. As a result, days become gradually longer while the moon moves farther away. The change is only a few milliseconds per century. No human life can notice it directly. Across geological time, however, the effect becomes meaningful. Long ago, the day may have lasted only 18 or 20 hours. Farther back, it was shorter still. Life evolved under days of different lengths. Ancient organisms experienced sunsets arriving more quickly. Their biological rhythms developed on a faster spinning Earth. The planet continues changing beneath the rhythms it created. The sun also changes its motion. It rotates, though not as a solid body. The equatorial regions turn more quickly than areas near the poles. This differential rotation twists magnetic fields. Those fields contribute to sunspots, solar flares, and cycles of activity. The sun's activity rises and falls over roughly 11 years. The cycle is not perfectly regular. Some periods are stronger or weaker than others. Solar storms can send charged particles toward Earth. When those particles interact with the atmosphere and magnetic field, they may create auroras. The light of an aurora is connected to events on the sun that began earlier. Particles need time to cross the distance between the sun and Earth. A bright display in the night sky may be the delayed result of activity that occurred days before. The sky contains many delayed consequences. Moonlight is reflected sunlight. The sunlight first traveled from the sun to the moon, then from the moon to Earth. The entire journey took a little more than 9 minutes. A quiet, moonlit room is illuminated by light with a small history. The photons left the sun, crossed space, touched the lunar surface, and continued toward Earth. Some entered the atmosphere. Oh! A few reached a window. Then they became part of this particular night. Starlight may have a much longer history. The light from Sirius takes more than 8 years to reach Earth. Light from Betelgeuse may travel for hundreds of years. When ancient people looked at those stars, they saw a different stage of the same distant suns. Generations share the sky, but not always the same light. A person centuries ago saw photons that had begun their journey before ours. Tonight's light began at another time. Future observers will receive light that has not yet reached us. The sky is renewed continuously, even when the stars appear unchanged. Every moment brings new photons from old sources. The image remains familiar because the changes are subtle. Continuity is built from constant replacement. A flame works in a similar way. The shape may appear steady, but new gases are always entering and leaving. The flame is a process rather than a fixed object. A waterfall seems like one persistent form, yet the water composing it changes every second. A river keeps its name while new water passes through. Many things endure because a pattern continues, not because the same material remains. Time reveals the difference between objects and processes. A mountain seems like an object, but it is also a process of uplift, weathering, and erosion. A cloud appears like an object, but air and water droplets move through it. A living body is a continuing pattern of metabolism, repair, and exchange. Even a thought is a temporary pattern of electrical and chemical activity. The world is full of forms that continue through change. This may be why time does not always feel like something moving past us. Perhaps we are part of the movement itself. We do not stand outside time and watch it flow. Our bodies, memories, and awareness are made from processes unfolding within it. Every breath is a small change. Every heartbeat marks another adjustment. Every moment of sleep belongs to the same ongoing pattern. There is no need to separate yourself from that movement tonight. You can be carried by it without effort. The clock does not need to be watched. The body does not need to be instructed. Light will continue crossing space. The moon will continue moving around Earth. The planet will continue turning beneath the quiet room. And your thoughts can become less distinct, like distant signals fading gently into the darkness between stars. Time becomes especially interesting when we think about speed. In everyday life, we move far too slowly for its effects to feel unusual. Walking, driving, or flying changes our passage through time by amounts far smaller than the body can notice. Yet the effect is real. A moving clock does not measure exactly the same interval as a clock at rest relative to it. The faster the motion, the greater the difference becomes. At speeds close to light, this difference can become dramatic. A traveler moving through space at enormous speed could return having aged less than people who remained on Earth. This idea is sometimes described through the twin paradox. One twin travels on a very fast journey. The other stays behind. When they meet again, they are no longer the same age. The situation is not truly a contradiction. The traveling twin changes direction and follows a different path through space-time. Their journeys contain different amounts of proper time. Proper time is the duration measured by a clock moving with the observer. Each person feels their own heartbeat and breathing as normal. Neither experiences time suddenly slowing inside the body. The difference only appears when the two clocks are compared again. This is one of the quiet lessons of relativity. Time can feel completely ordinary locally, while differing greatly across separate journeys. The universe does not provide one shared pace for everyone. Instead, each path through space-time carries its own duration. There's no need to picture the equations. You can imagine two gentle clocks moving along different roads and meeting again much later. Both kept perfect time. They simply traveled through different shapes of space-time. Particles reveal this effect clearly. Muons are unstable particles created when cosmic rays strike Earth's atmosphere. They exist for only a very short time when measured in their own frame. Without relativity, many should decay before reaching the ground. Because they move at speeds close to light, their lifetime appears longer from Earth's perspective. More muons reach the surface than ordinary timing would predict. This natural experiment happens constantly above us. Invisible particles cross the atmosphere, carrying evidence that time depends on motion. Particle accelerators show the same effect. Unstable particles moving near light speed survive longer in laboratory measurements. Their internal processes have not failed. Their passage through time differs from that of the laboratory. Technology must account for these effects. Precise clocks on fast aircraft and satellites accumulate tiny differences. Navigation systems correct them to remain accurate. Relativity is not only a theory for distant stars, it is present in machines quietly circling Earth. The speed of light itself remains constant for all observers in a vacuum. This is one of the foundations of special relativity. An observer moving toward a beam of light does not measure the light moving faster. An observer moving away does not measure it, moving slower. Instead, measurements of space and time adjust. Lengths contract along the direction of motion. Clocks differ in their measured rates. Events that seem simultaneous to one observer may not be simultaneous to another. The speed of light remains the same. This constancy is deeply different from ordinary motion. If a train moves toward you, its speed combines with your own motion in a familiar way. Light does not follow that simple rule. The universe preserves its speed by changing the geometry of measurement. At first, this can feel difficult to accept. Human intuition developed among slow objects. We understand thrown stones, moving animals, and drifting clouds. We do not naturally understand motion near light speed. Physics extends thought beyond the conditions in which intuition was formed. It allows the universe to be stranger than common experience. Strangeness does not have to be disturbing. It can be soft and spacious. A mystery can remain calm when there is no need to solve it before sleep. The idea of traveling into the future is already part of ordinary physics. Everyone moves forward through time. High speed simply changes how much future is reached relative to someone else. A traveler near light speed could cross a great distance while experiencing only a few years. When they returned, much more time might have passed on Earth. This would be a one-way journey into the future. It would not require reversing time. It would only require a path where less proper time elapsed. Reaching such speeds would demand extraordinary energy. For objects with mass, accelerating closer to light speed becomes increasingly difficult. The energy needed grows without bound as the speed approaches light. A massive spacecraft cannot simply cross that limit. Light itself travels at light speed because photons have no rest mass. They do not experience time in the ordinary sense used for massive observers. It is difficult to speak of a photon's own viewpoint. Relativity does not provide a valid resting frame for light. Still, the mathematics suggest no proper time passes along a light-like path. A photon may travel for billions of years according to our clocks, yet the interval along its path is fundamentally different from ours. This does not mean the photon has thoughts or experiences. It only shows that familiar ideas about duration do not apply in the same way. The universe contains several kinds of paths through space-time. Massive objects follow time-like paths. Light follows light-like path. Events too widely separated to influence each other directly are connected by space-like intervals. These categories define what can cause what. They protect the order of causality. A message cannot normally move outside the light cone. If it could, some observers might see the effect happen before the cause. This would create difficult problems for the consistency of events. Faster than light travel often appears in fiction. It allows characters to cross galaxies quickly. In known physics, however, it remains highly speculative. Ideas such as wormholes and warp drives appear in theoretical discussions. A wormhole would connect distant regions of space-time through a shortcut. A warp drive would change space-time around a vessel rather than pushing it locally beyond light speed. These concepts require conditions that may not be physically possible. Some would need forms of negative energy in unusual arrangements. No practical method is known. Even so, the ideas are useful for exploring the limits of relativity. Thought experiments can reveal where a theory becomes uncertain. They are not predictions that technology will soon achieve. Science often studies possibility without confusing it with reality. Wormholes are related to solutions of Einstein's equations. A mathematical solution can be valid while still being impossible to create or maintain in nature. The equations describe many imaginable geometries. The universe may allow only some of them. Determining which ones are real requires evidence. No confirmed wormhole has ever been observed. Black holes are sometimes mistakenly described as wormholes. A black hole does not provide a known passage to another place. Its interior remains hidden beyond the event horizon. The equations suggest complicated structures under idealized conditions. Real black holes may not preserve those structures. Rotation and charge can alter the geometry. Quantum effects may change it further. Our understanding becomes less certain near the singularity. A singularity marks a place where the theory predicts extreme curvature. It may indicate that general relativity is incomplete there. Physicists expect a theory of quantum gravity to provide a better description. This is another region where time may behave in unfamiliar ways. Near the center of a black hole, the usual distinction between space and time can become strange. Directions that once seemed optional may become unavoidable. Moving toward the future can become linked with moving deeper inward. The details depend on the type of black hole and a mathematical description. No observer can send information back after crossing the horizon. The interior remains inaccessible to direct study. What happens there is one of the quietest unknowns in physics. The universe keeps some regions hidden by causality itself. We can study their effects from outside. We can measure how stars orbit them. We can detect hot gas falling inward. We can observe gravitational waves when black holes merge, but the interior does not send us a complete story. Sometimes science learns from boundaries. A horizon tells us where information can and cannot travel. The cosmic horizon limits what has had time to reach us. The event horizon limits what can escape a black hole. A particle horizon marks the farthest region from which light could have arrived since the early universe. These boundaries are created by time as much as by distance. Two places may be separated, not because a wall stands between them, but because there has not been enough time for connection. The early universe faced this problem on a large scale. Regions now far apart appear to have nearly the same temperature. Yet in simple models, they may not have had enough time to exchange information. Cosmic inflation was proposed partly to explain this. Inflation suggests that the very early universe expanded extremely rapidly for a brief period. Before that expansion, regions now widely separated may have once been close enough to interact. Inflation would stretch tiny variations to enormous scales. Those variations later became the seeds of galaxies. The idea has strong theoretical support and matches several observations, yet many details remain uncertain. Scientists continue testing different models. The first tiny fraction of cosmic time is still difficult to reconstruct. Our evidence becomes clearer after the universe cooled enough for known physics to apply more confidently. Before that, conditions were extreme. For the earliest instant, existing theories may not be sufficient. The beginning of time itself is therefore not fully understood. The Big Bang model describes an early hot, dense state and the expansion that followed. It does not necessarily explain why there is a universe. It may not describe an absolute beginning in the philosophical sense. Some models suggest time began with the universe. Others explore earlier phases, cycles, or quantum origins. Evidence has not yet chosen a final answer. Asking what happened before the beginning may be meaningful in some theories and meaningless in others. It could resemble asking, what lies north of the North Pole? The question may assume a direction that no longer exists, or there may truly be an earlier chapter we have not yet learned to read. There's no need to decide tonight. The beginning can remain distant and quiet. The present moment does not depend on having a complete explanation of the first moment. A clock beside a bed can continue ticking without knowing the origin of time. A sleeping body can follow its rhythm without understanding relativity. Nature often works before understanding arrives. Stars shone long before anyone knew about fusion. Planets orbited long before gravity had a name. Hearts beat before biology described them. Sleep came before dreams were studied. You do not need knowledge in order to participate in these processes. Understanding is something the waking mind enjoys. Rest belongs to a deeper rhythm. For now, the ideas can become less precise. Speed can soften into distance. Distance can soften into darkness. The darkness can hold stars, clocks, particles, and quiet, unanswered questions. Each one can drift farther away from attention. There is no need to keep track of where the story has gone. You may already be missing small pieces. That is part of the movement towards sleep. Time can continue without being observed. The next minute does not require a witness. The room can remain still. The earth can continue its long rotation, and you can move gently through your own quiet path in space-time, one fading thought at a time. Some of the most precise clocks in the world do not use gears, pendulums, or visible hands. They use the regular behavior of atoms. Atoms can absorb or release energy only in specific amounts. When this happens, they respond to very precise frequencies of electromagnetic radiation. A clock can count those frequencies and use them as a steady rhythm. The official definition of the second is based on a transition within cesium atoms. Scientists chose this transition because it can be reproduced with remarkable consistency. No single atom needs to remember the time. The clock observes the shared pattern produced by many atoms under controlled conditions. Cesium clocks transformed modern timekeeping. They allowed laboratories in different countries to compare time with extraordinary accuracy. Yet researchers continued looking for even more stable systems. Some modern atomic clocks use atoms such as strontium or ytterbium. These are often called optical clocks because they operate at frequencies associated with visible or near visible light. Their oscillations are much faster than the microwave frequency used in traditional cesium clocks. A faster rhythm provides more divisions within each second. This can allow even finer measurements. Optical clocks are now so sensitive that small differences in height can affect their readings. A clock raised slightly higher experiences weaker gravity because time passes a little faster, farther from Earth's center. The two clocks can slowly move out of step. The difference is tiny, but advanced instruments can detect it. This means a clock can also act as a tool for measuring gravity. If the ground rises, sinks, or contains different amounts of mass, the local gravitational field changes slightly. Future networks of precise clocks may help scientists study volcanoes, underground water, and movements of Earth's crust. Timekeeping could become a way of mapping the changing planet. A clock may appear to do nothing more than count, but when it becomes precise enough, it can reveal motion, gravity, and structure. Precision often opens hidden layers of the ordinary world. A second seems simple until it is measured carefully. Then it becomes connected to atoms, satellites, mountains, and curved space-time. There is no need to hold these connections in your mind. You can let them pass like distant reflections on dark water. The water does not need to keep the image. It only carries it for a moment. International time is created by comparing many clocks. No single physical clock alone determines the time used around the world. Laboratories operate their own atomic clocks and share measurements. These signals are combined into a calculated timescale. Adjustments are then used to produce the civil time, followed by clocks, networks, and public systems. Global time is therefore a quiet collaboration. Many instruments contribute small pieces. No one clock must carry the entire responsibility. This cooperation is important because even excellent clocks have tiny imperfections. One may drift slightly because of temperature. Another may respond differently to its environment. By comparing many clocks, scientists can recognize and reduce these errors. Time becomes more reliable through agreement between independent measurements. The same principle appears throughout science. A result becomes stronger when it can be repeated by different observers. Precision is not only about better machines. It is also about careful comparison. Radio stations, satellites, internet servers, and fiber networks distribute timing information. Your phone or computer may adjust its clock without drawing attention to the process. Machines exchange signals and estimate the delays. They correct small differences so that events can be ordered consistently. Networks require this shared timing. Messages may travel through several routes before arriving. Systems need to know when information was created, received, or changed. In electrical power grids, precise timing helps monitor the movement of energy. In astronomy, observatories in distant locations combine measurements made at the same moment. In communications, timing allows many signals to share the same channels without becoming confused. Modern civilization contains countless invisible clocks. Most are never seen. They work inside vehicles, medical equipment, factories, financial systems, cameras, and scientific instruments. These clocks divide time into intervals far smaller than human perception. Yet human life continues at a slower scale. A conversation cannot be meaningfully rushed into a microsecond. A meal still needs time to cook. A body still needs hours to sleep. Technical precision does not remove biological rhythm. It simply adds another layer beneath it. The mind also creates internal estimates of short intervals. A person can often sense when a few seconds have passed without checking a clock. This ability is not perfectly accurate. It changes with attention, emotion, fatigue, and expectation. Fear can make moments seem extended. Boredom can make time feel slow. Absorption can make an hour disappear. The brain may use several mechanisms to estimate duration. Some theories involve accumulating neural changes. Others focus on patterns across networks of brain activity. There may not be one single internal stopwatch. Different kinds of timing may depend on different systems. Coordinating a movement requires timing. Catching a ball requires predicting where it will be moments later. Speaking requires placing sounds in the correct order. Walking requires muscles to activate in carefully arranged sequences. The nervous system manages these intervals without conscious counting. Music makes this ability especially visible. When people clap together, they predict a shared beat. They do not wait to hear the sound and then react. They anticipate when the next beat should occur. The brain is constantly making small predictions about the near future. Most of these predictions remain unnoticed. They help the world feel continuous and stable. When a sound repeats steadily, the brain begins expecting it. If the sound arrives late, the delay is noticeable. If it stops completely, the missing beat can still feel present. Silence may contain the shape of an expected sound. This is why a clock that suddenly stops can attract attention. The absence of ticking becomes more noticeable than the ticking itself. A repeated sound gradually moves into the background. The nervous system decides it is familiar and not urgent. This process is called habituation. It allows attention to move away from constant, harmless signals. The soft hum of a fan may disappear from awareness. A gentle rain may become part of the room. A steady voice may begin as something you follow and later become a calm background texture. This change can help sleep arrive. The mind no longer needs to examine every sound. It recognizes the rhythm as safe and predictable. Predictability reduces the need for alertness. The nervous system can soften its watchfulness. Not every person responds to rhythm in the same way. Some prefer silence. Others rest more easily with quiet, continuous sound. The common element is often the absence of sudden change. A sound that rises sharply may wake attention. A sound that remains gentle can become part of the sleeping environment. The brain continues hearing during sleep. It does not completely disconnect from the outside world. Important sounds, such as a familiar name or an unusual noise, may still be detected. But many ordinary sounds are filtered. Their meaning does not fully enter conscious awareness. Sleep is therefore not a complete absence of perception. It is a different relationship with incoming information. Time continues to be processed in this state. The brain moves through stages in an organized sequence. Certain electrical patterns appear during light sleep. Slow waves become stronger during deep sleep. Dreaming often occurs during periods of rapid eye movement. These patterns change across the night. The first cycles may contain more deep sleep. Later cycles may contain longer periods of dreaming. This changing structure is called sleep architecture. It is less like a single dark room and more like a quiet building with several levels. The mind moves through them without needing a map. Sometimes, a person wakes briefly between cycles. The awakening may be so short that it is not remembered. The body shifts position, adjusts temperature, or responds to a sound, then sleep continues. A night that feels uninterrupted may contain many small transitions. Memory does not preserve them, so the night becomes one smooth interval in retrospect. This is another way the mind simplifies time. It removes gaps and joins separate pieces into one story. Waking memory works similarly. You do not remember every glance, breath, or movement from yesterday. The brain preserves selected moments and allows the rest to fade. Without forgetting, memory might become overwhelming. Forgetting is not always a failure. It is part of how the mind creates order. Time removes detail, but it can also reveal pattern. A single difficult day may feel enormous while it is happening. Months later, it may become one small part of a larger period. The surrounding events give it context. Distance and time can change emotional intensity. This does not erase what happened. It changes the way the memory is held. Some memories remain vivid for many years. Emotional events often receive stronger attention and more detailed storage. The brain treats them as important for future decisions. Gentle, repeated experiences may be stored differently. 100 peaceful evenings may blend into one general feeling of safety. No single evening needs to remain clear. Together, they shape expectation, routine, can become a kind of memory held by the body. A familiar bedtime sequence may prepare the nervous system for rest. Lower light, quieter sound, and repeated actions become signals. The body begins anticipating sleep before it arrives. This is called conditioning. A place or routine becomes associated with a state. The association grows through repetition. It does not need to be forced. Small, consistent signals can become more powerful over time. Tonight may become part of that pattern. The voice, the darkness, and the unhurried ideas may tell the body that the active part of the day is ending. Nothing dramatic needs to happen. Sleep often begins through ordinary repetition. The same room, the same position, the same gradual release of attention. Time helps build these associations. One evening alone may not create them. Many evenings can. The body learns through quiet accumulation. A path appears because it is walked repeatedly. A rhythm becomes familiar because it returns. A habit becomes easier because fewer decisions are needed. This is another gentle use of time. Repetition allows effort to decrease. What once required attention can later happen automatically. Reading, walking, speaking, and many other skills begin slowly. Practice reshapes the nervous system. Connections become more efficient. The action becomes smoother. Learning is physical change spread across time. The brain is not fixed. It adapts throughout life. Some changes happen rapidly. Others require weeks, months, or years. Sleep supports this process. After learning, rest can help stabilize new memories and skills. The brain replays patterns of activity during sleep. This replay may strengthen useful connections. A task practiced during the day can feel slightly easier after a night of rest. The improvement may occur without additional waking effort. Sleep allows time to work quietly. You do not need to solve tomorrow during the night. The sleeping brain will not create every answer, but rest can change how problems feel. Morning may bring a little more distance, energy, or clarity. This is not because time magically repairs everything. It is because bodies and minds continue working through gradual processes. Hormones shift. Neural activity changes. Energy is restored. Emotional reactions may soften. The world may be the same, while the person meeting it has changed slightly. For now, there is nothing more to prepare. So, the clocks around the world can continue comparing their signals. Satellites can continue circling. Atoms can continue their precise rhythms. Your body can follow a much older and softer clock. Breathing can slow without being counted. Thoughts can appear with more space between them. The edges of each sentence can become less important. Time does not need to be perfectly measured here. It can become simple again. A quiet interval, a darkened room, a few distant sounds, and the gradual feeling that there is nowhere else you need to be. Long before clocks became precise, people learned to read time from the movements of the sky. The rising sun marked beginnings, while the deepening dusk signaled the approach of rest. The moon offered a slower rhythm. Its changing shape gave nights a pattern that returned again and again. A thin crescent grew wider. A full moon crossed the sky. Then the light gradually narrowed until darkness returned. These phases are not caused by Earth's shadow, except during a lunar eclipse. They come from the changing angle between the sun, Earth, and moon. Half of the moon is always illuminated by sunlight. From Earth, we see different portions of that bright half as the moon moves around us. One complete cycle of phases takes about 29.5 days. This cycle helps shape early calendars, ceremonies, farming traditions, and systems of navigation. The moon also changes when it rises. A new moon rises near sunrise. A first quarter moon is often high in the sky around sunset. A full moon rises near sunset and remains visible through much of the night. These patterns are predictable because the geometry changes gradually. The sky may feel mysterious, but many of its rhythms are quietly regular. Eclipses add another layer to lunar time. A solar eclipse occurs when the moon passes between Earth and the sun. A lunar eclipse occurs when Earth's shadow falls across the moon. Eclipses do not happen every month because the moon's orbit is slightly tilted. Most months, the moon passes above or below the necessary alignment. Over longer periods, however, eclipse patterns repeat. Ancient astronomers noticed these cycles and learned to predict future eclipses. One important cycle lasts little more than 18 years. After this interval, the sun, Earth, and moon return to a similar geometric arrangement. The eclipse does not appear in exactly the same place on Earth, but its general character can repeat. Time in astronomy often appears as layered cycles. A daily rotation sits inside a monthly lunar rhythm. The lunar rhythm sits inside the yearly orbit. Longer cycles slowly shift the positions and alignments of all three. The sky is never simply repeating. It returns in patterns that are familiar, but not perfectly identical. The seasons also follow Earth's changing position and tilt. Summer does not occur because Earth is much closer to the sun. It occurs because one hemisphere is tilted more directly towards sunlight. The sun appears higher in the sky. Days become longer. Sunlight reaches the ground at a steeper angle. 6 months later, the same hemisphere is tilted away. The sun remains lower. Days become shorter, and the light spreads across a larger area. Earth's orbit is slightly elliptical, so its distance from the sun does change. But this is not the main cause of the seasons. In fact, Earth is closest to the sun during January, when the northern hemisphere is experiencing winter. Seasonal time is shaped more by geometry than distance. Near the equator, day length changes only slightly throughout the year. Closer to the poles, the changes become extreme. In summer, the sun may remain above the horizon for weeks or months. In winter, it may not rise at all. These long days and nights alter the rhythms of people, animals, and plants. Life near the poles experiences time through large seasonal contrasts. Migration, feeding, and reproduction often follow changing light. Some animals respond more strongly to day length than temperature. The amount of light provides a reliable seasonal signal, even when weather varies. Plants also measure the night. Some species flower only after nights become longer. Others flower when nights become shorter. The plant does not read a calendar. It responds to biochemical changes created by repeated periods of light and darkness. Seeds may also wait through long stretches of time. Some remain dormant until moisture, temperature, or light reaches the right combination. Dormancy allows life to pause its visible activity. The seed is not inactive in every sense. It maintains the structures needed to begin growth later. Some seeds remain viable for years. A few have germinated after much longer periods under unusual conditions. Life can preserve possibility across time. Spores, eggs, and microscopic organisms may also enter states of reduced activity. During these states, metabolism slows dramatically. The organism waits for a more favorable environment. This kind of waiting is not conscious. It is a biological strategy shaped by evolution. In deserts, some small animals remain hidden until rain arrives. Plants that seemed absent can appear quickly after a storm. Temporary pools fill, eggs hatch, flowers open, an entire landscape changes its pace. For months or years, visible life may seem quiet. Then a brief season contains rapid growth and reproduction. Different environments create different experiences of time. In tropical regions, seasonal changes may depend more on rainfall than temperature. In forests, the opening of the canopy changes light on the ground. In oceans, currents and nutrient cycles create periods of abundance. In polar seas, plankton growth can explode when sunlight returns. Nature does not follow one universal seasonal calendar. Every ecosystem responds to its own combination of cycles. Ocean tides create another repeating rhythm. They are driven mainly by the gravitational pull of the moon, with an important contribution from the sun. As Earth rotates, many coastlines experience rising and falling water roughly twice each day. The exact pattern depends on the shape of the coast, the depth of the sea, and local geography. Some places have one strong tide each day. Others have two tides of different heights. Tidal rhythms shape entire communities of life. Creatures living between high and low water must survive changing conditions. They may be submerged, then exposed to air, sunlight, and waves. Many time their feeding, movement, or reproduction to the tide. Some marine animals can continue following tidal rhythms even when kept away from the shore. Their internal clocks preserve part of the cycle. The moon's influence enters biology through repeated environmental change. Spring tides occur when the sun, earth, and moon are aligned. The gravitational effects of the sun and moon combine, producing a greater tidal range. Neap tides occur when the sun and moon pull from different directions. The difference between high and low tide becomes smaller. These names do not refer directly to the season of spring. They describe the regular strengthening and weakening of the tides. The ocean rises and falls according to several overlapping motions. Waves may change in seconds. Tides change across hours. Currents may persist for days, years, or centuries. The deep ocean contains some of the slowest moving water on Earth. Large circulation patterns carry water through the global ocean. A deep water mass may travel for hundreds of years before returning near the surface. In that sense, the ocean contains water from different times. Some deep water last touched the atmosphere centuries ago. Scientists can estimate its age using dissolved gases and radioactive elements. The sea becomes a moving archive. It stores heat, carbon, chemicals, and traces of past climates. Ocean sediments preserve even longer histories. Tiny shells fall slowly toward the seafloor. Dust settles. Volcanic ash creates thin layers. Over time, these materials accumulate into a record. A core taken from the seabed may contain millions of years of environmental change. The deeper layers are generally older. By examining fossils and chemistry, scientists reconstruct ancient oceans. They can study temperatures, ice volume, and changes in marine life. The ocean floor receives history one quiet particle at a time. Lakes do something similar. In calm lakes, seasonal layers can form in the sediment. One year may leave a light layer and a dark layer. These paired deposits are called varves. Counting them can reveal the age of the sediment. Their thickness and composition can show how the environment changed. A flood may leave a coarse layer. A wildfire may leave charcoal. Dry period may alter the chemistry. A still lake can preserve events that occurred far beyond its shore. Peat bogs also store time. Dead plant material accumulates where water slows decomposition. Layer by layer, the bog grows. Pollen grains become trapped within it. Because different plants thrive under different climates, the pollen can reveal past vegetation. A tiny grain can remain preserved for thousands of years. It once drifted through air for only a brief moment. Then it entered a much longer record. Ice, mud, wood, coral, and stone all heap different kinds of time. No archive is complete. Each one preserves certain signals and loses others. Together, they allow scientists to compare separate histories. A tree ring may reveal a drought. An ice core may show a volcanic eruption. A lake layer may contain ash from the same event. When records agree, the timeline becomes clearer. Volcanic eruptions can create especially useful markers. A large eruption may spread ash across a wide region. The same chemical layer can appear in ice, lakes, and soil. Researchers can use it to connect distant records to one moment. Time that once arrived as a sudden event becomes a thin line in the earth. Meteor impacts also leave markers. A layer rich in unusual elements may spread across continents. Shock minerals and tiny glass droplets can reveal enormous energy. One famous boundary marks the time when many species, including non-avian dinosaurs, disappeared. The event happened quickly on geological scales. Its consequences unfolded over years, centuries, and millions of years. Time can be sudden and slow at once. A brief event may reshape the future for a very long period. A lightning strike lasts only an instant. The fire may follow. A forest may need decades to recover. A single mutation may occur in one organism. Across generations, it may influence an entire population. The duration of a cause does not determine the duration of its effects. Small moments can open long paths. Long processes can also end in a single moment. A star evolves for millions of years, then changes rapidly during its final stage. Pressure builds along a fault over decades or centuries. An earthquake releases it within minutes. A glacier moves slowly. Then a great piece breaks away in seconds. Nature combines gradual preparation with sudden transition. The mind does something similar. An idea may develop quietly for a long time. Then understanding appears all at once. The sudden insight depends on earlier work that was mostly invisible. A decision may feel immediate, though it was shaped by many previous experiences. A peaceful change may begin before you notice it. Sleep often follows this pattern. The body moves toward it gradually. Then awareness seems to vanish without a clear boundary. You may feel awake for several minutes. Then there is no remembered transition. Later, only the fact of sleep remains. There is no need to identify that moment tonight. It can arrive without being named. The moon can continue through its phase. The tide can continue rising somewhere far away. Seeds can remain quiet beneath the soil. Deep ocean water can continue its century-long journey. All these rhythms can continue without your attention. Time does not become lost when it is not observed. It simply carries on. The next few minutes can be allowed to pass in the same way, unmeasured, unhurried, quietly joining the long collection of moments that the night does not need to remember. As this quiet journey through time begins to settle, there is less and less that needs to be followed. The clocks can keep moving without your attention. The earth can continue turning beneath the night. Far beyond the room, the moon is moving slowly along its orbit. Its motion is steady, though no sound reaches us from that silent distance. The tides are changing along distant shores. Water is rising against rocks, slipping through sand and returning gently toward the sea. Somewhere, morning light is beginning. Somewhere else, evening is arriving. The same planet holds every hour at once. There is no single moment shared in exactly the same way by everyone. Yet all of these moments belong to one turning world. Time zones divide the map, but they do not divide the Earth itself. The borders exist in human agreement. Beneath them, oceans and continents move together through space. The planet does not know the names of the hours. It simply rotates. The sun does not count the years. It continues transforming hydrogen into light. The stars do not measure their age. They change according to gravity, pressure, and energy. Time passes through these processes without needing to be announced. A tree adds another thin layer of wood. A stone cools slightly in the night air. A cloud changes shape while moving beyond the window. Many changes are too small to notice. Still, they continue. The universe is rarely completely still. Even silence contains motion. Air molecules move through the room. Atoms vibrate inside walls and furniture. Light travels through darkness. The body continues its quiet work. The heart moves blood through vessels. The lungs exchange gases with every breath. Cells repair, organize, and communicate. None of this requires conscious direction. You can allow the body to continue on its own. It has carried you through every night before this one. It knows how to move from wakefulness into sleep. There is no need to find the exact path. There is no need to know how many minutes remain. The idea of time can now become simpler. Not atoms, not calendars, not relativity, only one soft moment, followed by another, and then another. You do not need to hold the moments together. The mind can release them as soon as they arrive. A word may appear and then fade. An image may form and disappear. A thought may lose its direction before reaching an ending. This is perfectly natural. Attention does not need to remain steady. It can drift like a small boat on dark, calm water. The current is gentle. There is nowhere it must reach. The boat can turn slowly without anyone guiding it. The surface can reflect a little moonlight, then the reflection can break apart and become darkness again. Time may feel like a river, but there is no need to stand on the shore and watch it. You are already moving with it. Every breath belongs to the current. Every fading thought moves with the current. Even sleep belongs to that same quiet movement. There is nothing more you need to understand tonight. The oldest stars can continue their long lives without being observed. Some will shine for millions of years. Some will remain for trillions. Their light will cross distances too large to imagine. It will move through empty space without urgency. A few photons may eventually reach a planet. A few may touch an ocean. A few may enter a quiet room. Most will continue into darkness. The universe has enough time for every journey. You do not need to travel with the light. You can remain here. The bed is supporting the weight of your body. The room is holding its familiar shape. The night is asking nothing from you. Sounds may come and go. They do not need to be identified. A distant vehicle may pass. A building may settle. Wind may move against a window. Each sound can arrive, remain briefly, and disappear. You can let it leave without following it. The same is true of thoughts. They may enter from nowhere. They may seem important for a moment. Then they can move beyond attention. There will be time for necessary thoughts later. Tonight they do not need answers. The future can wait outside the room. Tomorrow has not asked to be solved. It will arrive in its own way. Morning light will grow gradually. The sky will change before anyone commands it. The body will wake when sleep has completed enough of its quiet work. Until then, nothing needs to happen quickly. The night can remain wide and patient. You can rest inside it. Perhaps time feels slower now. Perhaps it has become difficult to tell how long you have been listening. That uncertainty is welcome. The clock can become less meaningful. Minutes can lose their edges. The difference between one moment and the next can soften. This is how sleep often approaches. Not as a sudden event, not as something forced, but as a gradual fading of boundaries. The room becomes less detailed. The body feels farther away. Words become sounds before they become meaning. Then even the sounds may begin to drift. There is no need to notice when this happens. The transition can remain unobserved. You may hear another sentence, or you may already be somewhere quieter. Both are fine. The story no longer needs to carry new information. It can become only rhythm, a slow voice, a gentle pause, a little space, another breath, another soft moment passing. The universe can keep expanding in the background. Galaxies can continue moving away from one another. Stars can continue forming inside clouds of gas. Planets can continue circling their suns. Earth can continue turning through darkness. None of these motions need your attention. They will continue whether you remember them or not. Time will continue whether you count it or not. Your body can continue breathing whether you listen or not. There is nothing left to complete. Nothing left to measure. Nothing left to hold. The past can remain where it is. The future can remain unopened. This moment can become quiet enough to disappear. The night is not waiting for an answer. The clock is not asking to be watched. The universe is not asking to be understood. It can keep shining softly in the background. It can keep moving through its ancient rhythms. And you can let your own thoughts become slower, softer, more distant. There is no need to follow the next idea. There is no need to remember the last one. The words can fade before they finish. The room can fade around them. Time can become only darkness, warmth, and rest. There is nothing more you need to follow. The universe can keep shining in the background. The earth can keep turning quietly beneath you. And you can simply sleep.